Hey Seth, how's it going? I'm doing well too. I was supposed to go to the gym today, but I didn't go. I can't wake up early enough. And I refuse to go later. Oh no! Oh god. Holy moly, jeez. Thank you for letting me know. What am I doing again? Co-working? Oh, brother. I should have a checklist. Check this, check this, check this before I go live. Oh my. Okay, I'm gonna erase this. How was the Magic last weekend? It was last weekend, right? I think it was last weekend. Last third game? Oh no. It was it was one of those versus three other people, right? Just really unlucky card draws, I see. Dang, even after mulligans? Damn, that sucks. Let's see. Did this. Okay. This is next. Okay. I'm waiting for my coffee to finish so I can start sipping on it. How's your weekend going? Let's see. What am I doing here? This should be rather trivial. A lot of the hard work has already been done. $2.39. Okay. The set function. Assigns length, not any length, not a length. Assigns length. TH to any interval Just realized my camera is like far away. All right, let me think. Mm, okay. It's better. This is better. Okay. Okay. All right, so the first thing is about the measurability of these things. So what did I do here? This is length. I think lengths were measurable, right? Or intervals were measurable. Where is it at? So to fix this, every interval is measurable. There it is, 2.25. Hmm. 2.25, that's the length. Set translation. Is this one, 2.26. And then unions are also measurable. Where's unions? I think it's this one. Countable unions are measurable. There you go. 22, right? It was 22? Yeah. Interval is measurable. Set translation, and then there is union. Okay. There more. Okay, we wanted the length to be the interval. That is outer measure stuff, I think. Yeah, 2.6. Translation invariance. 2.7. Wait a minute, no. Countably additive is literally in this section. I think it's right here somewhere. Oh no. Yeah, it's right here. We just proved it. Wait, I didn't even have to do the union then. Oh my. Yeah, I didn't have to do union. This is already captured in the last results, so this I can delete. Eh? What I have set twice? Set translation. Okay, there we go. Let's copy this. Measure. Um, I should just use the same wording. Okay, translation invariant. Three point 2.35. 2.35 and 2.38. Okay. 138. Hmm. How do I close this without having to restate everything? How do I close this? Just gonna shorthand it. The claim is proven. There we go. Which claim? This claim. Okay. There's that one. Then we have some set theory stuff that we could define. We're just gonna define it because I think this comes up a lot in this subject. So we might as well just have a definition for it ready. 2.3, 2.40. Okay. Countable collection of sets. Okay. Descending. Okay. All right. I think we're almost done with this section. This continuity of measure, and then what do we have after this? The Borel-Cantelli lemma. I think that's it. Hey, I proved this already. I didn't even know it was a problem in this book. Let's see. Okay. The the Borel-Cantelli lemma looks kind of short to prove. So maybe I can actually finish both of these. Okay. Continuity of measure. Oh, this relies on the previous theorem. So that's why it's short. Okay, so I guess let's try this one. Oh man, I hate it when theorems or results have like two parts to them. Okay. I say increasing. The heck? Ascending. Literally just defined that before. As an ascending. The measure of the union is the limit. Okay. Oh my. Okay. All right. Okay. This result's actually very, I mean, a lot of this stuff is familiar, but this looks almost identical to Axler's version. Let's see. Um, 2B. Wait, what the heck? That was 2B? I think it's this section. Measure space. Hey, there you go. It's this one. Measure of an increasing union. And then the measure of a decreasing union, intersection. He's the smartest boy you've ever seen. Oh my. Aren't you in a stream, bro? Are you watching me? Okay, let's see. This is yeah, so these are this is basically it's broken into two parts in this book. I'm sure the procedure is going to be the same. Okay. Yeah, there you go. First assume that one of them is infinity. Define. Okay, define A0 to be the empty set. Okay. Okay. So you basically chop up the set um, so that they're disjoint and um, yeah, this is just making sure that we get disjoint sets. Yeah, there's this joint right there. And they're the same. Okay. Did I show all of this already in, what is this? Section 2? 2C? 2C, 2C, 2C. Hey, it's that question. And here's a picture. Okay, did I show it though? I think I just used the picture to justify it. Okay, maybe what I can do is just kind of like work it out. Yeah, maybe what we can do is try to work it out instead of using pictures. Okay. All right, all right, all right. Suppose there is a K naught N such that okay. Okay, since a K naught is contained in the union, a K, the measure of a K naught, which I should probably put in the next line because I wanted to also show the infinity part. So that's then equal to the measure of the union. And then this is infinity. So the measure of the union is equal to infinity. Oh yeah, that's right. And we also have to show that MK, MAK is infinity for all k greater than k naught. And this is because of the ascending. So since AK is ascending, AK naught is a subset of, what do I call it? AK for all k greater than or equal to k naught. The measure of AK naught less than or equal to the measure AK and this is again where the infinity comes in. Thus, the measure of AK is equal to infinity for all k greater than or equal to k naught. There we go. Uh, so the measure of the union is equal to the limit. And I guess what I should do is I should put what they're both equal to kind of show. That's the infinity case, right? Okay, suppose the measure of AK is less than infinity. Okay, this is where we had to kind of go through the set theory stuff. Okay, we're defining A not to be the empty set because it's not defined at all yet. We only have A1 through we only have the index of the natural numbers defined. So we can define A not to be the empty set. Okay. All right, we're going to show that AK minus AK minus 1 is disjoint and that the union is the same. Okay. Consider CK K minus AK minus 1. Okay. How would I get disjoint? Disjoint means that the intersection is empty. Let N and M be in N. Okay, then Cn intersect Cm is equal to An intersect Am. You know what, why don't I do this? Since it's ascending, we should also establish some order between these two. N greater than M, okay. An, N minus 1. Okay. I'm hoping this turns into the empty set. But I am going to get my coffee real quick. Be right back. All right. I got my coffee at 12 p.m. Okay. Let's pray that this is disjoint. Can I do it using set identities? This is the same thing as an intersect an minus 1 complement. And this is am intersect am minus 1 complement. Okay. Okay. So we know n is greater than m, so what do we know here? We know that am is contained in an. We know this. Okay, so if AM is contained in AN, then AM complement, oops, an AN complement is contained in AN, AM complement. Or another way to say this is that a a n minus one complement is contained in a m minus one complement. Okay. So what do we have here? Okay, from this we have AM getting absorbed because of the associativity of sets. So I guess I should show this. So we have AN intersect AM intersect um, AN minus one complement. Man, I need to work on my handwriting. It's starting to bother me. AN minus one complement intersect AM minus one complement. Okay, and then from here, we can reduce this to AN. This is AN because of the containment. And we can reduce this to AN minus one. Okay. And this is supposed to be zero. This is supposed to be empty. How do we get empty here? I should shout out Chan. I think about it. I gotta get better at remembering to shout people out. He's already long gone, but if anyone's still here and likes watching Pokemon, should give him a follow. It's also his birthday today. Okay. All right. I can do this. I can do this. So A and feel like it's not, I feel like it's not empty. Eh? Okay, I need to draw this. Is it empty? Okay, so if this is n, and this is n minus 1, if we remove this, that should be, yeah, that should be different from this. This is m, n minus 1. They should be disjoint. So why am I tripping out here? an, did I do something wrong here? an minus 1, that is, they need to be disjoint. How am I going to get the disjoint out of this? An, am. Oh my gosh, no wonder. So stupid. This is not n, this is m. Because it's the smaller set that survives, not the bigger set. And this is n. Okay, yeah, that makes more sense. Okay, am survives, and an minus 1 survives because it's the smaller of the sets. Okay, let's see. Okay, these are for sure disjoint, but I need to figure out how do I show this. It should be involving the ascending again. How do I show this? Basically, this set here, I'm trying to show that this set intersect um, this set, which obviously they're not intersecting, is the empty set. So how do I do that? I guess I could do containment. Um, do I want to do that? Is there like is there something here that is like obvious? This is the same thing as am minus an minus 1. I think you can get it from just this. Let's see, let me try to form the argument. Am minus an minus 1. Okay, so if I will erase this eventually. Okay, so if if n if n is equal to n plus 1, then am minus an minus 1 is equal to am minus am, which is just equal to the empty set. So if there's just one integer off, it's empty. And then anything greater than that, if what did I say here? If m or n is greater than m plus 1, then n minus 1 is greater than m. So, okay. So I think I'm on the right track. I'm not 100% sure though. N minus 1 is greater than m. So a m is contained in a n minus 1. Right? am is contained in n a minus 1. And so thus, a m minus a n minus 1 is contained in a n minus 1 minus a n minus 1, which is just an empty set. And so this means that that's the empty set. Hey, I got it. So that is like the rigorous details of showing disjoint rather than drawing the pictures. But definitely drawing the pictures helps ground you. Okay, so we've shown disjoint. Now we just need to show that the unions are the same, and that's, I think, just set containment, and there's no way to get around it, I think. Okay. So what do I do here? What am I showing here? I'm showing that the union of AKs is equal to the union of CKs. So let X be in the union. I think this is easier than what I just did, of AKs. Then X is contained in AK or some K. I feel like I've done this argument. Did I not do it here? Yeah, this is literally what I did right here. I was like, I remember doing this. Let X be in the union. Okay. I just didn't show the disjoint. I was like, when I was thinking about doing this, I was like, I remember doing this before. Let X be in the union. X is in. The issue here was that there, just because it's an EK, like it's kind of tricky to show that it's in the the set difference. Um, so the idea here is that you kind of have to leverage the ascending part, and so it basically all it comes down to is finding like a minimum integer that X is contained in, and then it's kind of similar to um, it's not, I don't want to say too similar, but it's very similar to the square root of 2 proof, where you had to have the rational number in its lowest term. It's kind of like similar to that, because basically, if you're in E3, right? It doesn't necessarily mean you're going to be in this point of E3. You can be in here, so it doesn't necessarily mean you're in E3 minus E2. And so you basically you're basically establishing that X is in some sort of minimum where um, it is in the set difference, I guess. So if we're in E3, I mean, if we're in E2, we're also in E3, we're also in E4, we're also in E5, right? And so to avoid the the complication of the set being in E5 um, but not in E4, you have to establish a minimum, which is given by the ascending part. So because the sequence of sets are ascending, there's a minimum um, there's a minimum natural number such that X is contained in the set EJ. And since J is the minimum, X is not in EJ minus 1. So this is to ensure that it is in the set difference. So X is in EJ minus 1 for some J. And then this tells you that it's in the union. And then going the other way is super easy, because um, if it's in some set difference, it's in EJ. And then if it's in EJ, um, then it's in some then it has to be in the union of the EKs because it's in EJ. Without the other direction is much easier. So I'm gonna copy and paste this because I've already done this. I don't want to reinvent the wheel here. But I'm glad I got this set difference taken care of. That is nice. That was nice. Now I feel better about it. I honestly, whenever I do these proofs, I do not feel comfortable leaving my proofs um, partially completed. And by partially completed, I mean like having a picture instead of an actual set theory argument, I guess. Because I feel like the picture is like should be the first step. Like if you're not sure, the picture should be the first step. It shouldn't be the final product. Okay, so copy and paste this. I'm only worried if I copy and paste it that it's going to erase. Okay, sorry, I'm getting some messages that I need to respond to. Okay, that was cool. That's nice. Oh my, what is going on? What is this? Delete this. And then what I'm gonna do here is I'm just gonna kind of move things around. I'm actually scared to move things around. Like this, this note app is like, has been letting me down a lot recently. It's been deleting too many things. And the only thing that the thing that's been saving me is literally my streams. My streams have been saving me because I'm able to refer back to what I wrote, and I can copy down what I wrote from my stream. But it should not be deleting my stuff. Okay. Um, so there's that. Wait, I put this, it's not even finishing the proof. Okay, let's see. We've shown that it's disjoint and that the unions are equal to each other. What else do I need to do here? Oh yeah, okay. Let's continue. Okay. By result 2 point. This was the recent one. This is countable additivity. This is like result 2.38. Yeah, 2.38. By result 2.38. God, when all the heavy work has already been done, it's like feels so nice. Feels so nice just to refer to some theorems. This is equal to the measure of the union of CKs. I'm almost tempted to not write this down, the CK. I'm just going to write it down explicitly. Look at this union, bro. Look at this. Oh my. This what was this? K minus 1. Yeah. And then this is equal to the sum. Okay, my handwriting needs to fix itself. K is equal to 1. of the individual measures A, K, and K minus 1. Okay. So this is just equality of sets, and then this is where 2.38 is being used. Um, let's see. Okay, so why is this cut? Why does this cut off partially? Oh no. Let me move this. Oh, it's the page. Oh my. Okay, I just need to shrink the I need to zoom out. Because if I go up, the page kind of shift to the left and right depending on what page you're on. That's because of the way the way the book is formatted when you create the actual hard copy. Um, okay, so since all of the measures are less than infinity, right? They're all less than infinity. They're all measurable. Then we have um, the excision property that we can leverage here. So we have okay. Let's just explicitly state why. Since AK is measurable for all K, measurable, and measure of AK less than infinity for all K. By result, this was in 2.3, I think, excision. Excision, measurable sets, was measurable. Early? Excision, there it is. 2.13. My 2.13, this guy becomes this guy. Measure of AK minus measure of AK minus 1. There you go. All right. Okay, the measure of AK. Okay, we got this. And then they split up. We turned it into the definition of the limit because now we can use the partial sum or the finite sum to um, yeah, we can use the finite sum to basically show we have like a telescoping effect. So um, by the definition of by the definition of just do this. Should I just leave it like this? I think it's obvious what I mean. I don't have to like show an index. Do this. Definition of infinite sums. We have this is equal to the limit as k goes to infinity. K? No, not k. This is n. Limit as n goes to infinity. With the partial sums. And I could just copy and paste this. Oh, I'm still nervous about copy and paste. Which is equal to the limit as n approaches infinity of, so this is telescoping, right? So this is AM, or no, measure of AK minus the measure of A naught. Okay. Ah. And the measure of A naught is defined to be, well, it's not defined to be zero. It's zero because A naught is defined to be the empty set. It's A naught is equal to the empty set. The measure of A naught is equal to the measure of the empty set, which is equal to 0. Thus, this. I'm not going to copy and paste. Thus, the measure of the union the AKs is equal to the limit n goes to, wait a minute, huh? Okay, I'm confused. What did I do here? N. Yeah, this is supposed to be n. Why did I not change this? It's supposed to be n right here. Because we're plugging in n. Yeah. There you go. And then n is just an index, so we can just call this k. As k goes to infinity, measure of ak. Okay, that's that part. Okay. Cool. Okay, to prove 2, define dk to be b1 minus bk. Okay. Oh, I feel like I have to prove it's ascending now. Let dk equal to b1 minus bk for every k. Okay, now I need to show dk is ascending. So let's see. How am I gonna do this? Smart stream? How you doing, KK? I saw you didn't play Unite last night. What was that about? You're supposed to play Unite every day. Okay. Just not on stream, don't worry. As long as he played Unite. Whew. Guardian was shut down again? Oh, yeah. I saw shut down streaming yesterday. Did you get Masters already? Let's see. I did, yes. Oh, my. Second day. Holy moly. I played a little bit yesterday. I was filling it out, and the games are really bad. So I was like, I was like, I'm not gonna grind it just yet. Gotta wait for the games to not feel so bad. Okay. Now the real grind begins. Yes. Are you playing competitively? Are you trying to play competitively? I know the competitive circuit's about to start soon, I guess. Or is it? I think it's January. That dk. Okay, so I need to show that dk is dk is ascending. So let me write this here. I need to show this is contained in here. How's the smart math going? It's going. I'm getting a lot of progress. It just feels there's like a certain point that I want to be, and I'm still kind of far off from it. So it feels slow sometimes. Yeah, but we don't have a defender that has a chance to practice a lot of. We need a tank that has time. I see. Yeah, that's the one. The main issues about trying to form a competitive team is the time. It requires so much time. Okay. Let X be in DK. I think Rezi's playing right now, right? Do you know if Rezi's still playing? He's playing, I think, in the Battle Hub, one of the Battle Hub tourneys. Oh, he lost? Oh, that sucks. Either way, I'm going to Worlds to just um share the network MP. But it's going to be how getting there. Oh, I will most likely be at Worlds 2 actually. So we'll probably meet next year. I'll be there with my team. My team, what am I calling my team? What am I calling them? Um, the eggheads. DK, X is in DK. Um, check you out on the eggheads. Then X is in B1. And X is not in DK. There's going to be a lot of people going, I feel like. Yeah, I'm going because it's like 30 minutes away for me. So I'll be able to go. So hopefully a lot of people go and we can all like hang out or something, grab some coffee or milk tea if anyone has that. You're an hour and a half. Oh yeah, you're in Cali too. I keep forgetting. I'm in I'm in LA County, so it's like it's like really close to me. Unfortunately, yes I am, yeah. Well, there's good and bad, you know. The good is the weather. I don't know if that's good anymore, but I think comparatively to all the other locations, it's good. Since BK BK plus 1 is contained in BK. Like questionable weather. Yeah. I mean, sometimes it gets, I don't know. Sometimes it's just hot when it shouldn't be hot, you know? I prefer the cold. Oh, I see. Did you moved here? Or it sounds like you didn't grow up here. When it's nice down by you, the weather is still 90 plus by me. No, I think the weather is also like that for me. I think because I'm more eastward. I'm like more east from the coast. So if it's hot, it's hot. It's hot for me. Like if you're closer to the beach, obviously it's gonna be like 20 degrees cooler, which I wish it was for me. Oh, I moved on when I was 3. I see. I've been traveling every year back to Florida and outside of Cali. Oh, interesting. Oh, I know what else is out there. Yeah. Oh, that's interesting. You got to one day um talk about that in your stream. At least whatever you're comfortable with, because it sounds like an interesting story. And x is not in BK. So since BK plus 1 is contained in BK, x is not in BK plus 1. So x is in B1 minus BK plus 1. Oh, you talked about it? Porpinski sticks up for Cali, and I'm like, it's trash. Don't come here. We are overpopulated. Can't buy groceries and the traffic blows. Yeah, yeah, that's the you know all the bad parts of California. It's awful. The more eastward you go, the better it gets though. But more eastward you go, the hotter it is. Unfortunately, because the more deserty it is. And then there's also it's less what do they call it when they like it's not as developed in the east as well, so that's another negative. So I guess don't be in Cali. Don't have money to go to the places around. Yeah, it's expensive. Where would you go if you had the choice? Like, where would you move to? Thus, okay, plus one or okay. Okay, I showed it. I just showed this. Jacksonville, Florida, or any place I can get 50 acres. Interesting. Montana, Tennessee, Georgia. Wow. What's the goal with the 50 acres? Trying to get a farm or something? Trying to have real life Farmville? Let's see. Just have all doggos happy and don't come by my property unless you're invited. That's funny. I get that. I think going to South Dakota growing up just made me love that open space and just fresh air. I see. Okay, okay. You're also kind of far from your neighbors, right? Like, because of the large land. I know for me, sometimes when I go out, like if I'm about to like walk to a location instead of use my car, I kind of look outside my window to see if there are any neighbors. And if there aren't any, then I go. If there are, I stay and wait. There's literally a meme that I saw, I think 4 days ago, that explained, or that literally, like, that fit that mold. It was literally me. I don't know. I'm just so introverted. I can't. I'm very bad with like small talk. It's always like, oh, how you doing? I'm doing good. Nice. Um, how you been? I'm really bad with stuff like that. Says the guy who streams. How you doing? Oh yeah. Oh nice, Pen Center. Welcome, welcome. I didn't think you were gonna finish before me. Thank you for the raid, Pen Center. Let's see. La 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 la. I could do this. So, shop Pen Center. Pen Center also does math streams, and I think the occasional video games, from what I remember. So, if you are interested in that stuff, give him a follow. He's a great, great guy. Um, Don also streams. Speaking of Don, I don't know if I can do a shout out. So, does this work? Oh no! Follow Don if you can, if you're interested in math streams as well. Here's a short cooldown. Yeah, the Twitch one has a short cooldown, right? I was hoping that my Nightbot would do that. But thanks again for the stream. I mean the the uh the raid. The raid. I'm actually I'm actually waiting for Stooky to stream. I think Stooky is streaming in an hour. Am I right? Ran, you Italian? No. I actually get that quite often. Looks like he's about to start. I see. I see. I'm going to raid into Stooky when he starts his stream. Stooky just started. Oh no. Okay. Okay. Good timing because I'm literally at the end of my theorem. I'm literally at the end. So I'm gonna finish up my proof, and then I am going to raid into Stooky. But no, I'm not Italian. I get. Are you Italian? Are you white? What else do I get? Are you Armenian? Nice, nice. I'll see you there, Pen. Thank you, thank you. Um, yeah. And I'm none of those, to be honest. Let's see. Okay, I just showed ascending. What else is left? I've shown ascending. Okay, and then by part one, we can show this. One of us. Yeah, it's. I feel very welcomed in the community. Although I do stream a little bit more, a little bit more selfishly. I stream for the sake of analysis and learning it, I guess. A mean machine. I saw you yesterday, I think. Right when I ended my stream, actually. This is equal to the measure. So this is by part one, which we just proved. And then we have De Morgan's identities right here. This is equal to this is the De Morgan's identities. Okay. Okay. By De Morgan's. Sometimes it's good. Sometimes it's good. Sometimes it's no good. Oh my. Okay. Suki just started. Okay. I'm like literally. I'm right here. I'm right here in this theorem. So I'm about to finish up, and then we can rate Stuki. Hey, Wisdom Me. How you doing? Does anyone else have issues writing the union? Like a nice union? Mine's always comes out really messy. Okay, the union of dk is equal to the union of b1 minus bk. And then this is equal to the union of b1 intersect bk complement. And then this is where nothing about your handwriting is messy. When I see like these wiggles, like even if it's small, if I see like a small wiggle, it bothers me. Just sound like Joey from Friends. How you doing? I love Joey. Okay, so this is De Morgan's. So this is the same thing as B1. Um, okay, this is the same thing as the union of all the intersections, and then those. I think this is what it is. So it should come out like this, BK complement, and then this by De Morgan. So this is distributive properties, and then this is De Morgan's right here. Right? Is this what I needed to get? Oh no! What did I do here? This was... Joy's my favorite character. Minus Phoebe. Who do I like? I like Joey, and I also like Ross. This is how you do an emote? Yeah, 100% is. 100%. Okay, what did I do here? This is B1 intersect B1 complement. B1 intersect B2 complement. Okay. You could never help you on what you were doing. Just gotta spend time on it. Now's the time. Okay. The union. So how does this work? Do I need to prove this? Or is this something that's just a, is this literally a De Morgan identity? Hmm. Hmm. I don't see anything on Wikipedia about it. Okay, why don't we do this? Why don't we apply De Morgan's law from the beginning and see what happens? We apply De Morgan's, we get the intersection of B1 intersect BK complement. Oh, and then we get a complement here. And then if we do that, we get the intersection K equals to 1, and this becomes B1 complement union BK. What was it I was trying to prove? Trying to prove B1. I think I'm running into the same issue. B1 complement the union of BK. What was I trying to prove? Yeah. Oh, yeah. Okay, what's the general scheme here? So I'm noticing here that we got B1 complement union B1. That's just the universal set that we're working with. And so we end up getting B1 complement B2 union B2. And then the B's are also descending. If I had a dime for every time I've included my inductive hypothesis. Okay. Why am I stuck here? Why am I stuck? So B1 B1 is a decreasing sequence, right? So B1 is B1's the largest set. What is going on here? It has to do with the descending part. I'm pretty sure that's what it is. That's what's going on, math. And this is so tricky. Why is this B1 intersect B1 complement union B1 intersect B2 complement union B1 intersect B3. I don't really need to write this many terms, but this gives us empty set and B1 intersect B2 complement. This is where I'm struggling. B1 intersect B2 complement. B1 is the largest set. Intersect B2 complement. Intersect B2 complement. B2 is contained in B1. Hmm. This is B1 intersect B2 complement union B1. Intersect B1 intersect B2 union B3 complement. And then this becomes B1 union B1, which is just B1 intersect B1 union B2. All right, this doesn't look helpful. B1 intersect. Oh my. B1 is contained in this union. So this just becomes B1. Intersect this. What the heck, man? What is going on here? There has to be some De Morgan's identities for set differences. Uh, oh my, there is. I just missed it. Okay, I'm going to show what I'm about to use. I think it's this one right here. No, it's this one right here. It's this. And normally I would try to prove this. I would normally try to prove this, but this is like a standard set theory consequence. So I don't try to prove like some of the standard set theory stuff. Only like stuff that is probably kind of unique to this subject. So, but this is just, I mean, if you want to prove this, it's just set containment, which I was about to try to do, but like something in my head was telling me this is like a set theory, like a standard set theory problem. So this is literally the De Morgan's identity for set differences. So this is just equal to B1 intersect, oh, B1 minus the intersection. Okay. Which is what we wanted, right? This is what we wanted. Yeah. And then this is by result 2-point excision. Excision is here, 2.13. By 2.13, oh, right. Since BK is measurable for all K, the intersection is measurable. Something happened. Oh, Lobster Chung. Thanks for following. I'm officially leaving before I keep coining the coffee house jams. All right, KK. Take care. I'll see you later. Okay, so this is measurable. Cheers. This is measurable. I could refer to the result, but I'm just gonna say since measurable sets are closed under intersections. Oh my, thank you for letting me know. Oh man, I am not on it today. Holy moly, thank you. Okay, so the intersection of measurable sets are also measurable. And that has been proven in a previous section, but I'm not going to refer to it because I guess I'm just too lazy. So measurable sets are closed under intersections. And so we needed that to be measurable. What else do we need for excision? Excision also requires that the measure we're cutting out is finite. Is that said in here? Yeah, it's saying here, okay, it's not fully said, but it's partially said. So we can actually show that BK is, the intersection of BK is finite because the intersection of BK is a subset of B1. So since the intersection of BK is contained in B1, which is the largest set, the measure of the intersection is less than or equal to the measure of B1, which has been established to be less than infinity by the hypothesis. So and what I just reused was result 3 point or 2.4. I will say what result is here because that one is burned into my head. Result 2.4 and the hypothesis. And now we can use excision. So by result 2.13, I think it was. Is that tilde just a step subtraction over in the PDF? Yeah, yeah. So yeah, I don't really like this symbol, to be honest. Sometimes they use this, sometimes they actually use the actual minus sign. And sometimes they use the backslash or forward slash. I like this one the most. I like this one the most. I used to like this one, but then I realized that there can be confusion between set notations and differences in functions and stuff like that, or differences of what's the word, of field values. Yeah, yeah. That's the main reason why I hate it, because it's like this is what you're using for equivalence relations. So I hate that this is used in this book as set difference. So that's why I use this the forward slash or backslash. I don't even remember which is which. The slash. Yeah. It sucks because there's so many branches of mathematics that like there's advantages to different notations and different branches. Yeah, it's the symbol to use 100%. Yeah, for sure. Result 2.13. This is excision. So we've satisfied the hypothesis. We've shown that this is less than infinity and that the set that we're subtracting off is measurable. And so we can do the difference. The measure of B1 minus intersection is equal to the measure of B1 minus the measure of the intersection. Okay. Oh, they're doing DK. Oh my. The measure of DK. Let's see, what are we doing here? I think this is still fine. The measure of DK is equal to B1 minus the measure of BK. Yeah, I think this is still fine. Oh yeah. It's two. We're two of these. I think we got two of these. Or do we need both? No, actually we don't need both. We just need the DK. Yeah. Oh, did I do all this work for no reason? Union of DK. So this is. Yeah, I think a lot of this is unnecessary. We didn't. Not all of it's a waste, but for some reason, I thought we were going to go this direction. Okay, so I'm gonna kind of pull out what I don't need. Which is this part. Just in case I do need it for some reason. Okay, so since the measure of the intersection is finite, yeah, this is like overkill actually. It's just BK. Yeah, BK is contained in B1 for all K. And then this is the measure of BK. And then that's the hypothesis, okay? And that's what we want. That's what we're trying to show here. And then by result 2.13, the measure dk is just equal to the measure. And so dk is defined as b1 minus bk. This is equal to the measure b1 minus the measure bk. Nilo, I don't know how to pronounce your name to be honest. Nylonco? Thanks for following. Okay. So this is what we wanted to show. Nylonco. That sounds like a company. Nylonco. Okay, we've shown this. And so oh my, and I even wrote the wrong one here. This is DK, because this is DK that's increasing, not BK. And you know what? I'm gonna identify this as 1. And I'm gonna identify this as 2. By 1 and 2. I have no idea how to pronounce my name. It's chill. That's good. That's funny. Oh, it's nice to meet you. By 1 and 2, what we have here is, bruh, I thought I copied this app this app makes me want to rip my hair out. The measure of the union of dk is equal to the limit as k goes to infinity of the measure of dk And this is just the limit as k goes to infinity of the measure b1 minus the measure bk. Oh my gosh. What we're trying to prove here. We were trying to prove that the intersections. Okay. Oh man. Okay, this is fine. Okay, so I did still need this. I still needed this. Because we need to use excision on this too. Okay, so since BK is contained in, and I gotta move things around. Since BK is contained in B1 and the intersection is contained in B1. The measure of the intersection is less than or equal to the measure of B1, which is less than infinity. I didn't even erase this. I didn't even erase this, and thank God I didn't. Because if I erased it, I would have to write that in as well. So this is less than infinity, and this is less than infinity. So these two need to be established by result 2.4 and the hypothesis. They both are established by the same things. So by result 2.13, that's excision. We have this, and we have this. Call this 3. By 1 and 2, we get this. And then by 3, and set equality, the measure of the union of dk, which is equal to the measure of B1 minus the intersection of BK. That is equal to B1, the measure B1 minus the measure of the intersection. All right, I got it. Okay, then if we set them equal to each other, let's call this 4 and 5 by equality of 4 and 5. Oh, I hate copying and pasting. I wish this thing didn't glitch so much. I'm going to write this down. The measure B1 minus the measure of the intersection, BK, is equal to the measure, not the measure, the limit. The measure of B1 minus the measure of BK. And there's a small analysis, detail that isn't shown in this proof. So we're not allowed to say that the MB1s cancel. They do eventually, but we're not really allowed to say it yet. We need to show that the limit distributes first. So and the way we go about that is we show that since the measure, so since the limit as k goes to infinity of the measure b1 is equal to the measure b1, since it's a constant in this case. It's a finite constant. And so this is finite, and then this has to converge, the measure of bk. So do we have convergence of measure of bk here? What gives me convergence? Oh, there's convergence. We have it here. So since the limit itself is equal to this is finite and this is finite. Because we've already established this measure. We've established that this is less than infinity, this specific measure. And so this difference is going to be a finite. So the limit is also convergent, the entire limit. And the limit this is less than infinity, this means that this is less than infinity. So the reason why we can't say this is less than infinity, even though the individual BKs are less than infinity, right? We got that the individual BKs are less than infinity, but just because it's less than infinity doesn't mean that the individual ones can't blow up themselves. So um, we can't just conclude that this converges on its own. So the reason why it converges has to do with this converging because it's a constant and the total limit converging. And so that is applying this guy. So what we just applied here is that if one of them converge and the entire one converges, then the other one has to converge. That's what we just applied. I don't know if that's obvious. And then since the limit of that measure sequence is less than infinity, we can distribute the limit. And so hence the measure of B1 minus the measure the intersection BKs, that has to equal 2, and this is where the distributive part comes. So this is the measure of B1 minus the limit. This k goes to infinity of the measure BK, or measure of the intersection is equal to the limit. Okay. That was a lot of details I wasn't expecting. And that concludes the proof. All right. That's awesome. Okay, let's hop over to Stuki. Stuki should be doing a lecture right now. So thank you everybody. GG. GG. That was a lot more work than I expected. But that's why I'm doing this. For everyone that's still watching, thanks for watching. I'll be back probably Friday to do more of this stuff. And yeah, if I don't see you until Friday, I'll probably see you in another stream. I tend to loiter or lurk in other math streams. But I'll see you next time. And Stuki. I always get paranoid that I'm about to like raid into some random person that has a Twitch account that is similar to that has a similar name. Anyways, have a good day. Enjoy the lecture. Yeah.
See you around.